tungsten and alloyed with a little bit of rhenium for added ductility. We designed this femtosecond laser mill in-house to cut the features of the needle and cannula, and it can do this with sub-micron precision. We spent a lot of time this year turning this thing from a science project into an industrial system. Just a couple months ago, it took a skilled operator 22 minutes to make a needle, and even a skilled operator could only get about 58% yield. Today, that same process takes just 6 minutes, and anyone can get 91% yield with just a few minutes of training. With only one click, the mill cuts and measures the needle and cannula and uploads the measurements to our limb system so that the robots can use the exact dimensions for each needle that it uses. Just a couple months ago. Now, this is all for our current design mill. 22 minutes. And we've had a couple years to optimize the manufacturing process. It could only get about 58% yield. The current design has served us well so far. That same process takes it doesn't quite protect the thread well enough. Anyone can get 91% yield. Like I said, we had to come up with something new, and we needed to be able to iterate on only one click. The mill cuts and measures the needle and cannula. Unsurprisingly, there's no page in our machinery's handbook that the robots can use the exact dimensions. We dug into the science of femtosecond laser ablation and figured out a workflow that allows us. This is all for our current design laser mill. Much like we had a couple years to optimize the manufacturing. This allows us to only get about 58% yield. This design has served us well so far. The same process takes it doesn't quite protect the thread well enough. Anyone can get 91% yield. Like I said, we had to come up with something new. As a result, we needed to be able to iterate with only one click. Seen on the right, the mill cuts and measures the needle and cannula. Unsurprisingly, there's no page in our machinery's handbook that the robots can use the exact dimensions. We dug into the science of far more than we could ever expect in a human workflow that allows us. This is all for our current design laser mill. Much we had a couple years to optimize the manufacturing. This allows us to only get about 58% yield. This design has served us well so far. The same process takes it doesn't. The needle is not thread well. Anyone can get 91%. As you can imagine, like I said, we had to come up with something new. As a result, we needed to be able to iterate with only one click. Seen on the right, the mill cuts and measures the needle and cannula. Unsurprisingly, there's no page to our limbs handbook that the robots can use the exact. We dug into the science of far more than we could ever expect. This is all for our current design laser mill. We had a couple years to optimize the manufacturing. This allows us to only get about 50%. The design has served us well so far. The same process takes it doesn't. The needle is not thread well. Anyone can get 91%. As you can imagine, like I said, we had to come up with something new. As a result, though, is iterate with only one click. We can come up with many measures the needle and cannula. Unsurprisingly, there's no page to our limbs handbook that the robots can use the exact. We dug into summer weeds or even more than we could ever expect. This is all for our current design. Take this failure mode, for example. A few months ago, we got to the point where we could pretty reliably insert through the Dura. But when we took the proxies and put them in our micro CT imaging, we realized that our hold on the end of the threads was actually too strong, and we were pulling them out just a little bit underneath. So we can come up
structurally, just like effect robot insertion. Developed an bone, skin, or even a whole body. A brain proxy that simulates motion, vasculature, and electrophysiological activity, and a biological process. Cerebral organoids, as shown here. And all of this will get us closer to a future where we learn more and iterate faster on benchtop and reduce our reliance on animal models, or even one day replace them completely. And with that, I'll hand it over to Dan, who will be presenting a very exciting next generation application. Thank you.
Thank you, Leslie. My name's Dan, and I came to work at Neuralink after following a career in visual neuroscience research. I was inspired to join this company because I saw in our device the potential to restore vision to people rendered blind by eye injury or disease. There are a number of particular characteristics of our device that make it uniquely suited to this application. Firstly, as well as being able to record from every channel, we can stimulate neural activity in the brain by injecting current through every channel. This is important because it allows us to bypass the eye and generate a visual image in the brain directly. Secondly, our device can have an enormous number of electrodes. For a visual prosthesis, this is important because the more electrodes you can have, the higher density of an image you can create in the brain. Thirdly, thanks to our robot, we can insert these electrodes deeply into the brain. Now, this is an important thing for a visual prosthesis because the human visual cortex is buried deeply in a fold in the medial face of the brain called the calcarine sulcus. In this image, I've highlighted the calcarine sulcus in red in an MRI. It contains a map of the visual world, the visual field. It's about a surface area equal to a credit card on each side. And if you unfold it and flatten it, you see that the image is inverted, it's upside down. But more interestingly, it's distorted so that the central part of the visual field, the fixation point, is greatly magnified. So for example, if you look at this image of Lincoln, if you look directly into his right eye, everything to the left of that fixation point is directed to your right visual cortex, and everything to the right goes to your left visual cortex. His eye, even though it's very small in the image, distorted, it's so magnified in the central part of the visual field, the fixation point, quarter of the surface area of the visual cortex. Of Lincoln, over the last half century, directly into his right eye, visual neuroscientists have developed a profound understanding of visual processing in the brain. What's driven most of this research is recording from single cells in the cortex, usually of macaque monkeys. One of the seminal discoveries was that every cell in the visual cortex represents only a tiny part of the visual field. Your perception is made up of a mosaic of tiny receptive fields, each belonging to a single cell in your visual cortex. So if you record from one of these cells in a monkey, say in this location, you can find a very tiny region of the screen where a light stimulus will cause modulation of that neuron. Another location in visual cortex will have a location elsewhere on the screen, in this case in the lower visual field. These regions are called receptive fields. We've inserted our device into the visual cortex of 2 rhesus monkeys, whose names are Code and Dash. That means we can record activity from their visual cortex generated by their normal home environment as they roam around. But as we all know, monkeys love banana smoothie. That means we can easily teach them to fixate points on a screen and reward them. We can reward them very precisely because we can track the location of their eye using an infrared camera. One of the things this allows us to do is to plot the receptive fields for every neuron that we can record with a single device. Now we do this by showing the animal a movie of random checkerboards whilst he fixates steadily on the screen. Then we take only the frames of the movie that generated a response in the cell and average them all together. This is a technique known as reverse correlation. It's generally used quite widely in visual neuroscience for this purpose. And this is an example of a receptive field plotted with this technique. The central cross is the fixation point, and you can see the little red and blue regions of excitatory and inhibitory receptive field. These regions give cortical cells some of their characteristic properties. So we can record all the receptive fields from all the electrodes at the same time. And if we take all these receptive fields and accumulate them together, overlap them, and place them on a computer monitor for scale at a typical viewing distance, you begin to get an idea of how much of the visual field we can cover with this preliminary device. Many of the receptive fields are close to the fovea, close to the fixation point. That's partly due to the magnification that I talked about of the fovea. But there's also a scattering of fields in the periphery. These are from recording sites deeper in the brain in the calcarine sulcus. So far, I've only talked about recording information from the cortex. But to produce a visual prosthesis, we need to stimulate. So, if we stimulated the cells whose receptive fields are in this location, we would produce a perception of a flash in that location that only the monkey can see. How do we know that the monkey sees it? How do we know what it looks like? Well, unfortunately, we can't ask them what they see, but we can train them to tell us something about that phosphine. We start by training the monkey to fixate a central point on the screen, like this white dot, and we start by presenting real visual stimuli on the screen and rewarding the monkey for making eye movements toward those stimuli. So here we flash a white dot, and the monkey makes an eye movement towards it, symbolized by the green arrow. We then choose another random location and reward the monkey for making an eye movement towards it. Once he's got good at this task, we can begin to interleave these real stimuli with electrical stimulation of electrodes and produce a phosphine. The monkey sees the flash and naturally makes a saccade towards it. This tells us not only where in the visual field the flash occurred, but we can also change the current that we inject in that electrode to see how often he makes that saccade unnoticeable, or how big perhaps the stimulation of phosphine is that we're producing. Let's look at code performing this task. I want to show you first at 1/4 speed. There's a visual flash, and he makes an eye movement towards it. The monkey can only see what is white on this screen. He can't see his own eye movement. And he certainly can't see when we stimulate. But here we stimulate, and he makes the same saccade in the same location because we stimulated the same electrode. Nothing appears on the screen at that time, and he has no cue to make that eye movement. Let me show you this in real time. You can see the monkey looking like the very quickly. And when we stimulate, we make that saccade in real time.
contract, and in turn you have movement. While of course there are many other circuits involved in voluntary movement, you can think about the spinal cord as many pairs of these two connections. And in spinal cord injury, one of these connections is severed, unable to make the muscles contract. Let's zoom a little bit further. So here you can see on the left a cross-section of the spinal cord with a fiber coming down schematically. This travels through the white matter tracts. This is the upper motor neuron. And then it synapses within this butterfly-shaped region of gray matter in what's known as a motor pool. In the motor pool, the lower motor neuron descends out the ventral roots to the muscles, which contract. And then the sensory consequences of those movements, for example, the touch of your hand against an object, return to the spinal cord through the dorsal roots and ascend the spinal cord up into the sensory regions of the brain. Again, in spinal cord injury, this connection is severed. If we could place electrodes into the spinal cord, say in a motor pool adjacent to lower motor neurons, we could stimulate those neurons, activating them, and in turn causing the muscle to contract and movement to occur. But this is very hard to do. The spinal cord is quite delicate, and it moves significantly within the bony spinal canal. This could cause damage to the electrode, it could cause damage to tissue, or both. But our electrodes are small and flexible, and our robot is able to insert them deep into tissue, perhaps all the way down into the ventral horn of the spinal cord. And so we have done just that. Here you can see a view from the R1 robot. It's a targeting view, and we've placed electrodes across many millimeters of the spinal cord. And the R1 robot is able to insert those electrodes deep into the ventral horn, into motor pools, in very close proximity to lower motor neurons. This is important because it allows them to have a localized connection to those neurons and activate very precise movements. Now, to track movement, it's very common to use motion capture markers, like you might see in the production of a movie. These can be placed with a light adhesive, and you can see me placing these on my hand. We're going to use these markers to let us zoom in on movement in the next couple of slides. Okay, so here's a pig walking on a treadmill, and you may have seen something like this before in a previous Neuralink presentation. But unlike before, this pig has more than one Neuralink device. There's a device in the brain, but there's also one in the spinal cord. And we can stream neural data from this device, these devices, in real time and use them to do things like decode the movement of the joints of the pig. So here you can see on the left a time series of the hip, knee, and ankle, and we're decoding those movements. So this is super cool, but that's actually not what we want to do. We want to go in the other direction. We would like to stimulate the spinal cord and cause movement to occur. Okay, so let's do that. So here's a pig, a happy and healthy pig doing what pigs like to do, which is root around for food and snacks. And as you'll see on the floor, there's a blue square. This is a voluntary engagement zone where the pig places itself, indicating that it's comfortable to receive stimulation. When it's in this zone, we stimulate, and if the pig leaves this zone, we'll stop stimulating. And as before, you can see we're able to track the position of the joints and also stream neural data as well. Okay, so let's stimulate on an electrode. So here's one electrode on one thread that when we stimulate causes a flexion movement of the leg. So on the left, you can see the movement of the joints, and you can also see the time series of the stimulation pattern in yellow. So the leg is moving up. Here's another electrode, which when we stimulate causes an extensor movement. This is actually a little harder to see because the leg is straightening and the hips are shifting, but if you look carefully, you can see how the leg is moving. We can stimulate on a great variety of threads and produce different movements and actually sequence them spatial-temporally to provide patterns. So on the left, you can see a time series of different stimulation on different electrodes. You can see the movements of the joints. And on the right, we're zooming in on muscle activity that gives us an idea of the kind of strength and power and specificity of those movements as well. So in addition to doing sequences, we can also achieve sustained movement. These are powerful muscle contractions of the sort that you might need for standing or other load-bearing activities and are really crucial for interacting through the world. Okay, so stimulating the spinal cord is only one piece of the story. You also have to get command signals for the stimulation of the spinal cord. Unfortunately, we have a way to do that. We have the N1 link that you've already heard about placed in motor cortex. How would that work? So we place threads in motor cortex and record spikes. These spikes would be wirelessly transmitted in real time and decoded into patterns of stimulation. Stimulation would then be delivered to the ventral horn of the spinal cord, to the appropriate motor pool for the muscles that we'd like to activate. We then activate those lower motor neurons, which causes the muscles to contract and movement to occur. Now, of course, movement without sensation is actually kind of difficult. Just think about what it would be like to try to move your limbs if they're numb. But we can also get sensory information as well. So the sensory consequences of your movement can be recorded in the dorsal horn of the cord in the form of spikes. For example, here, a feather touching the hand. These spikes can in turn be decoded in real time, sent to patterns of stimulation to either the same N1 device in the brain or perhaps a different one in a sensory area. Stimulation of that part of the brain would cause percepts of touch and proprioception, closing the loop. So putting those two loops together, we have motor intentions to stimulate the brain, causing perception. Now, we have a lot of work to do to achieve this full vision, but I hope you can see how the pieces are all there to achieve this. And if you find this prospect as exciting to you as it is to me, I hope you'll consider
really all the things that we listed in the Neuralink/careers. That'd be a good guide.
Yeah, I'm actually very fond of saying, when you flip through any college like booklets and look through all the majors, I think you can point to every single one of those majors, and there's someone at this company who either is an expert or have majored in that. So it really is truly multidisciplinary endeavor, and I think just focus on whatever you're passionate about or whatever you're talented at, and then just pursue that as deeply as you can, and then there's definitely going to be a place for you in building neural interfaces.
Hey. We got to see the monkeys doing telepathy, but could you say a little bit more about the animal behavioral training, kind of their lives and day-to-day processes?
Sure. I'm Autumn. I am head of research services, which includes our animal care program. And as an animal welfare scientist, this is a topic that I'm deeply interested in. So our training program is outfitted mostly with behavior analysts who help us think about how to remove any of the potential aversives or frustrations from our training. We think about conditioning as the primary, which includes positive reinforcement, as the primary way to train. Let's see, what else can I share with you? Yeah, I mean, that may not be part of the behavioral training itself, but we think of animal welfare assessment in the framework of the 3 R's, which is refinement, replacement, and reduction. And so when we think about refinement, behavioral training does apply in that way, and where we want to remove, specifically in research, restraint is one of the things we make a very top goal to remove. So you saw a lot of videos today where animals were walking up to their stations because we worked really hard to remove any requirement to restrain the animal. Anything else?
Yeah, if I could just, well, just on top of the last point you said, just as an engineer here, one of the things that is really inspiring and really cool about this place is that we do get to work on a lot of technological innovations that directly translate to greater independence for the animals when they're engaging in these tasks. So as you saw, monkeys charge just by voluntarily walking up to a branch. They play games in their home habitat with a laptop computer voluntarily. And the fully implantable, fully wireless device, the inductive charger, all these things enable that kind of experience. And so this is one of the very cool parts about working here is we do get to innovate on things like that.
Definitely helps to work with a group of engineers who can really make cool stuff for monkeys to be able to do easier behavioral training.
Yeah, so I guess to answer the previous question about what you can study to be part of Neuralink, I guess monkey engineering you can add to that.
Monkey business.
Monkey.
Hello. Oh, it's on. My question is on upgradability, which you guys mentioned quite a bit. So in that procedure, I imagine there's some kind of explant procedure, and then you're going to put in a new set of implants. So could you talk about the damage possible, if any, tissue damage from the explant procedure? How long you have to wait? Do you implant in the same areas? And what's your brain scanning for the implant procedure in terms of upgrading it? I don't know how many questions I can ask, but I have one more after this too.
So I can start to speak to some of those. So I work a lot on upgradability and those explant processes and designing those to be better. The goal that we're working towards is that, as I mentioned in the presentation, it's really just as easy to upgrade an implant as it is to initially install. Examples today, but we've come pretty close to just popping out an implant and reinstalling another one in the exact same location. Definitely the goal, we are installing the implant in primary motor cortex, which is a valuable area for interacting with a device like this. And so the goal is to implant in the same location. Maybe if you expand out to other applications, then you'd be interested in moving somewhere else. But we definitely want to be able to insert into the same area. In terms of damage, I think that the damage that we care most about is damage within the brain. And what we've found, and we talked about that challenge of the tissue layer on top of the brain, and I think we're well on our way towards figuring that out. But because of the thread's small size, the sort of scar capsule within the brain is so minimal that they are actually removed quite easily. And so we see useful signals even on the second or third time that you've placed an implant. And I think some of our BCI folks can probably speak to that. We do have monkey participants working with their second devices and really making use of those.
So two questions. One was somebody had asked the question about the brain being plastic. Have you noticed any plasticity from a behavior perspective from any of the monkeys? Or is it too soon to tell, or there haven't been any observations?
From the monkey behavior, we see that it takes them a while to learn how to, of course, to train on the task, but also when they are reimplanted. It's relatively quickly for them to ramp up and get to a high performance of brain control. With Pager, for example, after a few days, he was able to, like 3 days already, able to learn very quickly to use the device. He was trained on the task, of course, from his previous implant, but with the new one, after 3-4 days, he was able to control to close to performance of he had with the previous implant.
But have you noticed anything on the adverse side, which means the brain has outpaced the neural network that you're running?
It's hard to say.
No, not really.
Okay. So I have another question, which is more about the electrical side. So you talked about 1024 channels being recording. Are you transmitting the raw signal, or was it only the 3 spike events that you were talking about, the low, mid, and the high? Or is it the entire raw waveform that you transmit?
Yeah, hi, I'm Julian. I can speak a bit about this, and maybe Avinash wants to contribute. But our chips see the raw signals, but then when we transmit out, typically spikes, and we detect those spikes in real time on the chip. This massively compresses the data. I guess, yeah, we're making improvements to that, but we can request raw samples. Sometimes we also process particular statistics or other data directly on the chip and then send out the calculated values. So there are many ways to sort of play with the data.
Yeah, so at least with the current N1 system that we have, which relies on BLE radio, there is a bandwidth limitation, so you can't actually stream raw data from all 1,024 channels. But just kind of to give you a little bit of a history of how our compression algorithm, the spike detection algorithm, was developed. We did have sort of a wire system. There was a paper that we published with the USB-C connector that streams all those signals through a high bandwidth wire connection. So we did have kind of those development platform to be able to see the raw signals and know which set of information that we want to extract that are going to fit within the bandwidth of the radio, as well as is useful for BCI control. And also just sending data wirelessly does cost a lot of energy. So there's any opportunities we have to reduce that burden. We try to basically have all that compression closer to where the electrodes are as possible.
Maybe one thing that isn't obvious is that the actual bit rate that you need to control a phone or a computer is actually very, very low. So I think we might have the record for bit rate. Is that correct? We think we do, maybe. So on the order of 10 bits per second. So that's super slow. But if you think when you're inputting data into a phone, like how fast your thumb's moving, what's your thumb taps per second? Pretty low. And I mean, we're like basically, our thumbs are like two slow-moving meat sticks that we, do this, and it's like, it's really low, it's like a low bar, is what I'm saying. So at least for output, you get 10 bits per second, you're hauling ass. And that's, you don't need Bluetooth anything for you. So you could practically send it out with beeps and bops, So it's not, if you're going like high bandwidth visual, now you're maybe going to megabit plus, but it's still really well within Bluetooth. But anyway, it's just that is what I'm saying is that's not a constraint, the data rate. One of the sort of like maybe notable item which we talked about in the presentation, but we think we can probably solve for doing the implant without cutting the dura. We can just do basically a bunch of holes through the dura, which is like the dura is like the big thick orange rindy thing that contains that's up against the skull. If you don't pierce the dura, if you don't cut the dura away, and instead you have a bunch of tiny holes and insert the electrodes through the tiny holes into the brain, then the recovery time is ridiculously fast. You're not really losing much in the way of cerebrospinal fluid. You could, in theory, this could be like the whole thing could be a 10-minute operation, like LASIK. Like, it's fast. It's not like a big laborious thing. It's super fast.
Just going back to the long-term use, I'm wondering if you have any pathology looking at scar tissue from any animals that have had long-term implants. And along that lines, it seems like there might be a little bit of a gap between use in medical conditions and healthy individuals from a safety perspective.
Sorry, I didn't quite catch the last question, but I heard the first one. I'll ask you to repeat the second one. So the first one is, do we have pathology from long-term use animals? We absolutely do. We don't have any pathology from our monkeys, which we upgrade and are still going. We have other studies that are primarily to determine safety, and so we do have histopathologic endpoints that we determine. The scar tissue formation around the threads themselves in the brain is typically negligible, like it barely reacts to the threads at all. So that's very promising. In terms of the scar tissue formation over the cortex, so this neomembrane growth that fills in the areas that Elon and Alex were mentioning that we remove with our current operation, those we do evaluate that scar tissue, but it doesn't pose a problem in any way. It's not a continuous reaction to a foreign body. It's just filling in tissue that was removed. And if you could repeat the second question, I didn't hear that.
Yeah, the second question, really following up on that, seems like there might be a little bit of a gap in use in healthy individuals from a safety perspective. I think people mentioned that they might be interested in trying prototypes, but just wondering what your perspective is on trying to lower the safety risks.
Yeah, it's a great question. So in terms of, really it's about the long-term use of the device. So we have devices that have been implanted, like I said, in monkeys where, for many years where we see no behavioral deficit at all. So this first is a question of how you evaluate safety. So you have histopathologic endpoints you can evaluate, but we're also looking for cognitive deficits or behavioral deficits as well. And we don't see any of those in our animals, which is an important point. In terms of the histopathologic endpoints, they look really, really great. The challenge is one of explanting the device, which is why we're putting so much effort into the reversibility efforts and our through dura insertions. So when removing the device, that's when you potentially could cause damage. And so we have a lot of ongoing studies right now to really minimize the risk of that. But we don't think it's a substantial risk with our current approach. And like I said, Pager was upgraded with the previous surgical approach and is doing great. So clearly it is, can be perfectly safe, but proving that beyond a shadow of a doubt for humans is something that we're still working to do rigorously. Did that answer your question?
Yeah, thank you.
So thank you for a very deep dive on many of the different aspects of the device and the system. It's very impressive to see all of the engineering work that's gone into it. You just mentioned about bitrate. As the prior bitrate holder, I can confirm you have indeed shattered my record. So congratulations on, I think I saw a peak of 7.4 bits per second. Well done. My question is actually around clinical trials and the FDA. To the extent that you can share, I gather that device removal or maybe electrode removal is one of the concerns that the FDA highlighted. Is there anything else you can tell us about what the FDA was concerned about or had questions about with respect to their IDE submission?
Yeah, I mean, we can probably talk a little bit. I mean, these are really challenges, that we have broadly. So, explantation safety, proving that rigorously for humans is something that definitely is one challenge and was something that the FDA commented on. Other things that they do ask some really great questions. So other things involve things like the thermal benchtop testing of our implant. So obviously it's important that our implant doesn't damage the tissue by overheating. So having really rigorous and valid benchtop testing for that is very important. It's actually something that we're redesigning to be even more accurate now. It's also the case that they ask a lot of very hard questions on biocompatibility, chemical characterization. So we've done very rigorous testing for that, but they do ask a lot of questions about getting into the weeds of the data and making sure that there really is no chance for any toxic chemicals or bioincompatible materials to be in the brain. So these are all things we're working with to just prove, again, above and beyond a shadow of a doubt. One thing that's maybe worth mentioning here is that it can be difficult to appreciate the novelty of our product. So the surgical robot and the thin film array in particular are quite new and unlike existing devices, and this means that we can't rely heavily on literature to support the safety and efficacy of the device. So we do spend a ton of effort in designing and performing testing on our devices so that we can rigorously prove the safety of them, and we can't rely just on another product or on some paper. And that's something that we're not willing to compromise for our first human participant, and working very hard to do.
I think if you ask a question like in my opinion, would I be comfortable implanting this in someone, one of my kids or something like that? If at this point, like if they were in a serious, like let's say they, if they broke their neck, would I feel comfortable right now doing it? I would. I would say we're at the point where, at least in my opinion, it would not be dangerous.
Hi, thank you for the presentation. So I have a non-technical question. Are you collaborating with people with motor disabilities? And if so, have they shared any ideas of applications that they would be excited about?
I can take the first part of this. I'm not the best person to speak to this, to be honest, but there is a consumer advisory board we have made up of a number of people that have various conditions, including tetraplegia, and they give advice to us on a number of topics. There was, just as an anecdote, someone came to the office maybe 6 months ago, and they were telling me what they most wanted to do with their Neuralink device, and there were two things that they said. One was they wanted to be able to trade stocks day to day, to be able to beat their brother. And the second one was they wanted to be able to play shooter games. So I think what was most shocking to me about that encounter was the normalcy of that. And I found that conversation truly inspiring. So you know who you are, the person who came and talked to me. Have a great day. Yeah.
Wow, really? Shooter games, that's what we want to play. That's literally what we want to play in our minds.
Something that's we've talked about, but it's maybe it should be reemphasized. We are doing we're building up a production system for the devices. So we're bringing out the production line, making large numbers of devices. We want to make thousands, ultimately tens of thousands, then millions of devices. So the progress at first, particularly as it applies to humans, will seem perhaps agonizingly slow, but we're doing all of the things necessary to bring it to scale in parallel. So in theory, it should progress should be exponential.
Okay, so thank you. That was a very cool presentation. So one of the stated goals was recording from everywhere in the brain, being able to record from and perturb any location. So it seems like currently it's all cortical. And I'm curious, with the current device, is there any sort of long-term goal or idea as to extending it into going deeper in the brain? I mean, for neuropsychiatric disorders, for memory, all of these things are much deeper, several centimeters. So I'm wondering, what's the time scale, if you were to give a very rough estimate, of when I can expect to see a Neuralink product that goes that deep?
Yeah, so, I mean, the fundamentals of the device in the skull will stay essentially the same, because as I said earlier, the device in the skull is very much like a smartwatch. Essentially, it's a battery, radio, inductive charger, computer, and then you've got the little wires. And so you need to make the wires longer, and you'd have to have a deeper insertion needle for the robot. But this really is intended to be a generalized I/O device. So apart from the tiny wires being longer and the surgical robot needing a longer needle, in theory, you should be able to go anywhere.
Because it seems to me that part of the robot is trying to detect where the blood vessels are and then avoid them, correct? Would that be possible at that scale? I mean, certainly not just visually, but maybe there's some other way of detecting it. Is that a current goal, and do you expect that within, I suppose, the next decade?
Definitely, yeah. So I'm Ian. I run the robotics and surgery engineering team here. Of the 3 axes that DJ mentioned, one of them is, access to more areas of the brain. So the robot team thinks about this a ton in terms of what sensors do you need to essentially go past the surface. And so in this case, you're right that right now we can really only see down the maximum about 1 millimeter. I think within the team, there's questions of what's best to use next, but like ultrasound and photoacoustic tomography are 2 that come to mind as things that can get centimeters deep, essentially. But it's a super interesting problem. You sort of need deep imaging and some ability to steer to at least avoid large vasculature deep down. Yeah.
Or if we can make our needles and threads small enough in a way that we can still be precise and accurate at a deep depth, then maybe you don't cause a bleed if you hit a vessel.
Yeah, I think that's really the ideal situation. If the threads are really tiny, they can actually go through a blood vessel, and it's okay if they're tiny enough. So we wouldn't need the blood vessel imaging in that case. I actually am slightly optimistic that is achievable.
And Matt could probably speak more into this, but with DBS currently, it's kind of just like send it.
Yeah, the current approach involves a wire that you blindly pass in that's massive compared to our threads, orders of magnitude bigger. And so that's a low bar for us to clear as well.
I guess people don't realize, like, for the deep brain simulation, just how big the hole is. What is it, like? I mean, how basically, in current deep brain simulation, how much of a borehole is drilled in the brain?
Yeah, you're drilling a 14 millimeter burr hole and then passing a 2 millimeter wire, 6 centimeters, 8 centimeters deep into the brain. So all blindly, hoping that you don't hit a blood vessel, telling the patient up front, this might be good for you, and there's a 1% chance your brain is going to bleed in a way we can't control. So
that is current technology that is happening right now. So doing better than that is we can definitely do way better than that. There's no problem.
Our needle's 40 microns diameter.
Yeah, exactly.
Thanks again for the phenomenal presentation. I thought it was fascinating how rapidly you could test all of these electrodes, but it begs the question about like what your fault tolerance is. If you run these diagnostics and it comes back that you have something that's either shorted or high Z, how many of those before you get degraded performance? And the second question is when you're actually inserting this device, we saw examples of the electrode going in and then like looping back on itself, but it looked like that was something that was assessed basically by slicing the synthetic material. I'm curious what you're doing to validate the insertion of all these electrodes sort of in vivo. How do we know that that's not happening on an actual patient?
Yeah, I can answer that the second one. So like I mentioned, we can, so we weren't actually sectioning in that case. We have a really cool micro CT. It's essentially like a CT scanner. So that's just an intact proxy that we put in this machine, and we can, take a picture all the way through it. And like I mentioned before, like we can make a proxy where it happens, that looping back happens every single time, and then we can make one where it never happens. And we've pinpointed roughly now where actual tissue falls in there. And so our current plan for validating and confirming that is making proxies where it happens really easily, much worse case than any tissue could possibly be, and then designing it such that it never happens in that scenario. And that'll give us the doing that enough times and with a weak enough proxy, that'll give us the confidence that this isn't actually happening. Yeah, and this is the next gen needle. We don't see this problem at all with the current generation.
And I'll take a stab at your first question. So to clarify, you're asking what happens if there's a fault on a particular channel or something?
Yeah, that's correct.
Yeah. So the nominal scenario is that basically the impedance will stabilize pretty quickly within the brain, and even at that level, we can record great signals. We see lots of spikes, and we can use that for BCI. Because we have so many channels, like 1,000 now, 16,000 later, we can actually run our models with far less channels than we actually have. So it doesn't matter if like one channel dies here or there, like we can still do really good decode. I'm not sure if we have official numbers on how many channels we need, but it's like we have an order of magnitude more. And the more we have, the better, but we can already do a lot with what we have.
All right, maybe just one or two more questions.
Yeah, I have a question about your very, very long-term inspiration to have this high bandwidth communication with advanced AIs. So it seems like the advanced AI would need to understand the human's most complex thoughts and emotions, and that's what neuroscientists are trying to do. So do you have any ambitions to tackle neuroscience beyond neuroengineering?
Well, I mean, I think we're going to make the input-output device and the software interface with it, and I think probably, per the suggestion earlier, we'll try to open source as much as possible so people can take a look at it, and I think there will be a lot of others that build upon the work that we're doing. The same way that if you make a microprocessor or CPU or computer, that people will write lots of software that runs on that computer. But if you don't have the computer, the software is moot. So we're making the input-output device with the computer, and then I think probably there'll probably be a lot of other organizations, companies that build upon that foundation. So, yeah. I mean, one of the things that's I would sometimes wonder is that if you do have a whole brain interface and you can record memories, you're really getting into Black Mirror stuff here, but this could be one of them.
I also think it's worth mentioning an important point, which is that Neuralink didn't come out of nothing. There's decades and decades of research in the medical academic field that has really set the foundation for what is possible by putting these electrodes in parts of the brain and being able to read those signals, decode it for mapping it to some application. And being in academia before coming to Neuralink, I do think that there's a lot of opportunities for kind of the field to advance at a much rapid rate by having just better tools for observing the dynamics that are happening and then engaging with it in a seamless way. And I think it was Ian who sort of mentioned that it's almost as if like we're kind of building an oscilloscope for the brain, which I think is like kind of a beautiful analogy of just giving us a bit more abilities into peering into the dynamics and using those information, learn that to, I don't know, hopefully understand like what makes us and how the brain works and the whole shebang.
Hello. The presentation covered keyboard and handwriting-based input methods. How do you plan to develop an input model that will achieve much higher bandwidths for complex tasks in humans?
Yeah, this is a tough question, and we start exploring this with monkeys. As you saw, we have like we train many monkeys on very different tasks. It's still an open question that we're after. I think hopefully once we get to our first participant, it will be easier to investigate. One of the options we are exploring, as we showed, is to decode handwriting directly. This is a work that started at Stanford, and we are exploring here and trying to expand. There's also different, in addition to just decoding different things from the brain, we also try to provide the user different, maybe user-like interfaces. For example, we show different type of keyboards, maybe also swipe and other things that can help increase the communication rate. So we are kind of tackling those in 2 dimensions.
Yeah, just one other thing to add in that direction. As pointed out by many people here so far, this is a general I/O system that you can sort of plug and play in different places in the brain. There's other areas of the brain that can help increase bandwidth, for example, language or speech centers that can help you much more seamlessly communicate, for example, text, if that's your main thing that you're trying to do.
Yeah, I think just having this general input-output device will just so gigantically improve our understanding of the brain. It's hard to, the words can barely express. Like, right now we're just guessing a lot of what's going on in the brain, but if you have direct I/O, it's no more guessing. What we will learn about the brain with such a device in wide use is absolutely many orders of magnitude more than we currently understand. So I guess on that note, thank you for coming and thank you for watching online. And,
well, that's it. Looks like this is over. Have a good night for all of you watching, because there's one watching, and that's me. So enjoy the rest of your evening, everybody. Dr. GTI.